All right, so we're starting with section 8.1. Chapter 8's kind of a mixture, a hodgepodge of what seems to be a lot of different things that are not really attached to one another, but that's not really the truth. They actually are very interrelated with one another. We're going to start off with a review of things that we have talked about in the past or should have, and that is sequences. A sequence is just a list of numbers written in an explicit order. In other words, it has to be in a certain order. If the same exact numbers are put in a different order, then it's a different sequence. A sequence has to be defined and have a defined order to it. So here, notice this is set notation with the little pointy brackets. This is set notation of all the terms of a sub n. And this equals a sub 1, a sub 2, a sub 3, a sub n plus 1, etc., all the way to a sub infinity. So that is a sequence. This is an infinite sequence, as a matter of fact. We'll talk more about that in just a little bit. But this is the nth term. That is one way that you can describe it, and also a way that you can define the sequence. Any real-valued function whose domain is just a subset of the positive integers is a sequence. Now, you'll notice here the 1, the 2, the 3, all the way through. These are all integers, and that's what it's talking about here. Any real-valued function that you can only put in integers in, positive integers for the domain, is technically called a sequence. If the domain is finite, in other words, countable, that's another word for finite. Think about it as being countable. No matter how big the number is, if you can actually count to that number, it's a finite situation. Then the sequence is called a finite sequence. In calculus, we're going to mostly be concerned with infinite sequences. That means that the numbers are not countable. We're going to go off to infinity. There are infinite number of terms to that sequence. And that's primarily what we're going to deal with in calculus. If you're talking about a finite sequence, you're just talking about arithmetic. Now, it may be a lot of calculations, but it's just arithmetic. You're just adding them up, or you're just finding out what the next one is, and you're finding out things about the list of numbers. If you're talking about infinite sequences, that's where calculus comes in. Now, a sequence is defined explicitly if there is a formula that allows you to find individual terms independently. In other words, if you wanted to find the fifth term, if there is an equation or a formula that you can use to just plug in 5 for n and find that value, that is defined explicitly. For example, here is an example of an explicitly defined function. They tell you that a sub n is negative 1 to the n power over n squared plus 1. If we wanted to find a sub 5, we would just go over to this side and plug in a 5 here for n and a 5 here for n, calculate what we get, and that would be the fifth term. Now, notice this on top. This on top you're going to see a lot. Negative 1 to the n and negative 1 to the n minus 1 or n plus 1, either one. This is what's going to happen with this is that when n is even, we're going to have a positive term. When n is odd in this case, we're going to have a negative term. That's all this thing on top does, is it changes the sign. Now, if we had n plus 1 or n minus 1 here, it would be exactly the opposite of what I just said. If n was even, the plus 1 or the minus 1 would make it odd, thus we would have a negative term. And the same thing if n was odd, the plus 1 or the minus 1 would make it even and make it a positive term. So this top here, the negative 1 to the n power or the n minus 1 power, is going to just alternate the signs for this thing. So to find the 100th term for this, we could just plug in 100 for n. We're going to get negative 1 to the 100. That's an even power, so that means that the top is going to be a positive 1. 100 squared is 10,000, plus one more would be 10,001. So we end up with a positive 1 over 10,001. So that is defined, that's a sequence that's defined explicitly. And this is called the nth term expression. All right, now a sequence can also be defined recursively. And it's defined recursively if there is a formula that relates the current term that you're working on to previous terms. For instance, let's say our B1, B sub 1 is 4, and B sub n is B sub n minus 1 plus 2 for all n values greater than or equal to 2. So what that means we're going to do here is to find greater than or equal to 2. So we're going to find B sub 2. That means that B sub 2 minus 1 plus 2 is what we're looking for. Well, what is 2 minus 1? Well, 2 minus 1 is 1. So we're looking for B sub 1, which we know to be 4. It's already defined, plus 2. So we end up with 6. And then for B sub 3, we end up with B sub 3 minus 1 plus 2, just this equation again, and 3 minus 1 is 2. B sub 2 we found to be 6, and 6 plus 2 gives you 8. That is what a recursive formula does. The next term, the value for this term we're working on, is dependent on previous terms. It doesn't have to necessarily be the one just before it. And you have to keep going this way until you get the term you need. It's not just a plug it in and find out what it is, because it's based on previous terms. All right, now an arithmetic sequence has a common difference between the terms. Difference, of course, means subtraction. So that means if you take one term and subtract the term that came before it, you're going to get a number. If you subtract the next term minus the term before it, you're going to get the exact same number for a given arithmetic sequence. For example, if we have the sequence -5, -2, 1, 4, and 7, when we look at this one, what is -2 minus -5? Well, -2 plus 5 is going to give you 3. 1 minus -2 is going to give you 3. 4 minus 1 is going to give you 3. And 7 minus 4 is going to give you 3. So the common difference, signified by a lowercase d, for this sequence is 3. Now, if we had the natural log of 2, natural log of 6, natural log of 18, natural log of 54, we can still calculate this the same way. We're just going to do this term minus that term, or that term minus this term, or this term minus that term. We're going to do one term minus the one behind it. So, for instance, let's do the natural log of 18 minus the natural log of 6. Well, remember your log rules, your log properties, and that means that if we are subtracting two log expressions with the common base, we can make that into a quotient. So 18 divided by 6, which gives you the natural log of 3. So that is your common difference in this case, the natural log of 3. Now, arithmetic sequences can be defined recursively, and that was simply a sub n equals a sub n minus 1 plus d, and with whatever sequence you were doing, you would have to be given the first term, and all we're going to do is take that first term and add the common difference. Then we're going to take that term and add the common difference, and add the common difference to get the very next term. Now, they can also be defined explicitly with an nth term expression that is this: a sub n equals a sub 1 plus d times n minus 1. Now, the a sub 1, it's almost like a recursive one, except for the fact a sub 1 is always going to be a sub 1. It's not going to change. It's not just the previous one, but you have to give yourself a starting point. It's kind of like the c when we're doing our integration. We have to find out one place where it starts and then build from there. So we're going to find that first term, and then we're going to add multiples of d each time. Now, the reason this is n minus 1 is because when you plug in, let's say we're finding a sub 1, it's just a sub 1 plus d times 1 minus 1, which is 0. You don't want to add that d for that first term. And then it's going to pick up adding the common difference with the second term and every term after that. That's why it's n minus 1. Don't forget the n minus 1. The only way you can get around not using an n minus 1 is if you actually start off with a sub 0. And there are situations where that does happen. So you have to know what the thing is starting off with. All right, now a geometric sequence has a common ratio between the terms. Not a common difference, a common ratio. And remember, a fraction is a ratio. So it's just one thing divided by another. So for example, with this sequence, we would look and see what is the ratio between this term and that term, or that term and this term, or this term and that term. And all we're going to get to find there is negative 2 over 1, 4 over negative 2, negative 8 over 4, and 16 over negative 8. Well, if you look at those, that's negative 2, that's negative 2, that's negative 2, and that's negative 2. So all these are actually equal, and they equal negative 2, which is our common ratio, signified by a lowercase r. Now don't get this confused with radius. That's a common a little r that signifies the common ratio with a sequence. All right, and this one we get 10 to the negative 2, 10 to the negative 1, 1, 10, etc. Same thing here. We can find the common ratio by dividing. So let's use the 10 to the negative 1 divided by the 10 to the negative 2. Now you can do this and simplify by moving them and changing the signs of the powers, but it's easier just to go ahead and subtract. So remember, when you're dividing, all you're doing is what? Subtracting powers. Top power minus the bottom power. So this is 10 to the negative 1 minus negative 2, which means we're adding 2, and it's 10 to the first power, which is 10. So all we're doing here is multiplying by 10 to get to the next one. And if you know 10 to the negative 2 is 1 over 100, times 10 is 1/10, times 10 is 1, times 10 is 10, then it's easy to see. Now, geometric sequences can be defined recursively also, and that means we're going to take the term before and multiply it by r. So a sub n is nothing more than the previous term times r. But you can also define it explicitly with an nth term expression of a sub n equals a sub 1 times r to the n minus 1. And once again, that n is minus 1. We have to subtract the 1 for the same reason we have up until this point with the common difference. You don't want to multiply by r for that first term. You want to start multiplying for the second term and the third term and the fourth term to get the next one and the next one and the next one. All right, so here's an example. If the second term of a geometric sequence is 6 and the fifth term is 48, find an explicit rule for the nth term. All right, so what we're going to do is we're going to define each one of these by what they are and by the nth term expression. So a sub 1 times r to the fourth power, and that would be what? 5 minus the 1, that's where the 4 comes from, for the fifth term, and it's equal to negative 48. On the bottom, we have a sub 1 times r, which is going to be for the second term, 2 minus 1. Now, notice here, your a sub 1s are going to cancel out, and your r's, you can actually do the division there. R to the third is going to be equal to negative 48 divided by 6. So r to the third is equal to negative 8, and r would equal negative 2. So there's your common ratio. Now you just have to work backwards and find what the first term is. Well, that's actually not too hard to do either. If you know that a sub 2, you know what it is, it's 6, and it equals to a sub 1 times r to the 2 minus 1. Well, 2 minus 1, of course, is just going to be 1. So you can put a negative 2 there. You can put a 6 here, and then the only thing that's unknown is a sub 1. So a sub 1 is 3. So putting everything together in this form right here for the nth term expression, you're going to get what? A sub n equals negative 3 times negative 2 to the n minus 1 power. Now, guys, don't forget your basic arithmetic and algebra, and know that the only thing that is raised to the n minus 1 power is the negative 2. The negative 3 is not. It's multiplied after the fact. So make sure you remember that and follow those rules of calculation. The PEMDAS, the order of operations, still important, still part of math. Don't forget them. All right, now you can determine if a sequence converges by finding the limit as n approaches infinity. Now, let's talk about what converges means. Converges means that the sequences, the terms of the sequence, are going to approach a certain definite number as the number of terms gets larger and larger and larger. That's why finding the limit as n approaches infinity works, because you're actually finding what that sequence converges to. So for a sequence to converge, as you add more and more and more and more and more terms, or get more and more terms, those further terms down the list, a sub 1 million, a sub 10 million, those are going to get closer and closer to a certain value. If they do, then the sequence converges. If they don't, if they go off to infinity, negative infinity, or jump all around, then the sequence will diverge. Diverge means that it does not approach a certain value. So let's go ahead and find one and determine, does a sub n, if a sub n is 2n minus 1 over n, converge? Now it's going to converge if I take the limit as n approaches infinity and I get a number. So let's find out. So we've got the limit as n approaches infinity of 2n minus 1 over n. Now if you plug infinity here, you're going to get infinity over infinity. That doesn't work. We can do some simplification. What I'm going to do is I'm going to take that n and I'm going to divide it into both parts. I'm going to break it up into two parts and then take the limit. So I'm going to take the limit as n approaches infinity of 2n over n, which is 2, and negative 1 over n, which is minus 1 over n. Now remember, if you take the limit of this, you can think about this as taking the limit of the 2 and the limit as n approaches infinity of 1 over n, and then just subtracting them. So what is the limit as n approaches infinity of 2, and what is the limit as n approaches infinity of 1 over n. Well, as n approaches infinity, what is going to happen to 2? Well, absolutely nothing. So that's just going to be equal to 2. So this part just gives me 2. And what happens as n goes to infinity here? On the bottom of this, the bottom's getting larger and larger and larger, and what's happening to the overall value of the fraction? Well, it's getting smaller and smaller and smaller, so that's going to approach 0. So that means that this series is going to converge to 2. All right, now the absolute value theorem for sequences says this. It says if the absolute values of the terms of a sequence converge to 0, then the sequence converges to 0. Now, where we looked at the convergence before, remember we actually could find what that series or that sequence was going to converge to. Okay, notice with the absolute value theorem, it says nothing in here about whether or not we're actually finding the value that that sequence will converge to. All we're determining here was, does it converge or does it not? Does it converge to 0 or does it not converge to 0? And that's it. We're not actually finding if it's going to be able to converge to 2 or 7 or anything like that. We're only talking about, will it converge to 0? So if the absolute value of the terms of a sequence converge to 0, then that sequence will also converge to 0. Okay, so an example here, let's say we've got determine if a sub n equals -1 over n raised to the second power will converge to 0. All right, so using the absolute value theorem for sequences, we can actually go in here and we can take the absolute value of it. And if we do that, we're going to get rid, sorry, that's not right. Let's do that. Yeah, let's do it that way. So let's change this to n. So that means that it's alternating signs. So we take the absolute value. We take the absolute value of a sub n. That means we're going to take the absolute value of -1 over n to the nth power. So if we do that, that's going to strip the sign out of this. So it's going to be the same thing as 1 over n to the nth power. So then we can take the limit as n goes to infinity of 1 over n to the n power to see if this thing converges to 0. And what happens when n goes to infinity? Well, n to the n power, not only is that going to be 1 over infinity, but it's going to be 1 over infinity to the infinity power, which is going to be really big, which means this is going to go to 0. So yes, a sub n equals -1 over n to the n power will converge to 0. So that's all that this really is used for, is if you've got something that's alternating, you can use the absolute value theorem for sequences to strip that sign out so you don't have to worry about the pluses and the minuses. And if that thing converges without the signs, then it's guaranteed that it is going to converge with those signs. Now, if you plot any sequences, which the calculators will do, make sure you change it back to function mode. I'm not going to show you how to do it because it's not that important, but if you go and you can look at YouTube videos or Khan Academy videos and learn to do that if you want to. Like I said, I don't ever do it, so that's one of the reasons I don't teach it. That's it.